Welcome back, everyone, to another deep dive. Today, we're going to be looking at some really fascinating math.
Oh, yeah.
A recent paper actually called KP Integrability of Non-Perturbative Differentials.
Absolutely.
Now, this paper is going to assume some pretty high-level math.
Yes, definitely.
But don't worry.
Yeah.
I think we're going to be able to break it down.
Yeah.
So we can all understand what's going on. So
exactly.
To give you a quick overview, we're going to be talking about what non-perturbative differentials actually are.
Oh.
We'll discuss why they're important.
All right.
And the main thing this paper is trying to show is how these non-perturbative differentials are connected to something called the KP hierarchy.
Absolutely. Yeah, that's the core of it.
Okay, so to set the stage a little bit,
Mm-hmm.
I'm assuming everyone listening is familiar with Riemann surfaces and meromorphic differentials.
Right, of course.
But just as a quick reminder, a Riemann surface, it's basically a surface that locally looks like the complex plane.
Mm-hmm.
And we're going to be talking about genus in this deep dive. And the genus of a Riemann surface is essentially the number of holes it has.
That's a good way to visualize it.
Yeah. So like a sphere has genus 0.
Right.
A donut has genus 1.
Exactly.
And then you can just keep adding holes.
Mm-hmm.
Now, meromorphic differentials, those are a little more complicated.
A little bit more technical.
But essentially, they're objects we can integrate along paths on these Riemann surfaces.
Right.
And they have some special properties that make them really useful in complex analysis.
Absolutely. They encode a lot of geometric information about the Riemann surface itself.
Okay, so that's our kind of geometric background.
Okay.
Now, let's talk about this KP hierarchy business.
Right.
So KP integrability, what does that even mean?
So KP integrability refers to a system of differentials possessing a very special property. It means that they satisfy an infinite set of partial differential equations known as the KP hierarchy.
Ah, okay.
And this hierarchy is like a hallmark of systems that exhibit a kind of hidden structure, a deep underlying order.
Okay, so it's a sign that something interesting is going on.
Exactly. It's a clue that there's some intricate mathematical machinery at work behind the scenes.
So then this paper is looking for that clue in these non-perturbative differentials.
That's right. The authors are trying to show that these differentials, which are constructed in a very specific way, actually fit into this framework of KP integrability.
Okay, I think I'm starting to get the big picture here, but let's break down some of the key players a little more.
Sure.
What exactly is topological recursion?
So topological recursion is a powerful mathematical tool that allows us to generate systems of meromorphic differentials.
Okay.
And you can think about it as a recursive process, a sort of recipe,
Right.
where you start with some initial ingredients.
Okay, what are those ingredients?
So typically you'd have a Riemann surface.
Right.
You would have a pair of functions on that surface, often denoted as x and y, and a special object called the Bergmann kernel.
Okay.
And this Bergmann kernel, it essentially captures some geometric information about the Riemann surface itself.
All right, so we have our Riemann surface, we got our two functions x and y, and we have this Bergmann kernel, which is telling us about the geometry of the surface.
Exactly.
Okay, and what do we do with all that?
So you feed these ingredients into this recursive process.
Okay.
And it churns out a whole family of meromorphic differentials.
Wow.
And these differentials, they're neatly organized by their genus and their order.
Interesting.
So it's a very structured way of generating these objects that are important for understanding the underlying Riemann surface.
So we have this recipe and it just spits out all these differentials.
Yes, it's like a mathematical machine that produces these fascinating objects.
Okay, that's pretty cool. But what's the connection to non-perturbative differentials?
That's where things get really interesting. The paper actually focuses on a special kind of setup called the standard setup of topological recursion.
Okay.
And in this setup, we have these special points on the Riemann surface called key points. And these key points are crucial because they're the points where the differential of the x function, so dx, vanishes.
Okay, so we have these special points where dx equals 0.
Exactly.
And why are they so important?
Now, a previous result showed that the differentials generated by topological recursion, they're only KP integrable.
Oh, okay.
When the underlying Riemann surface has genus 0.
Okay, so only for really simple surfaces.
In a sense, yeah, when there are no holes.
So what happens in higher genus cases? When the Riemann surface is more complicated?
That's the real mystery.
Yeah.
And that's where these non-perturbative differentials come into play.
Okay, so these non-perturbative differentials are kind of a solution to this problem.
In a way, yes.
Yeah.
They provide a way to extend this notion of KP integrability to higher genus Riemann surfaces.
Okay. So what are these non-perturbative differentials? How are they defined?
So they're defined as formal power series in a parameter.
Okay.
And their leading terms, those terms that dominate as goes to zero, are given by what we call Krichever differentials.
Krichever differentials, I'm not familiar with those.
So Krichever differentials, they come from a beautiful construction in mathematics called the Krichever construction.
Okay.
And this construction links solutions to the KP hierarchy with geometric objects called Krichever data.
Okay.
And this Krichever data, it consists of a Riemann surface, a line bundle on that surface, and a distinguished point.
So it's a package deal. A Riemann surface with some extra goodies.
Exactly. And this package is intimately tied to solutions of the KP hierarchy.
So these non-perturbative differentials, they're built using these Krichever differentials as a foundation.
That's the key insight. The authors cleverly merge elements of this Krichever construction with the input data of what we call generalized topological recursion.
Okay, so it's like they're taking the best of both worlds.
Yeah, they're combining these powerful tools to create these new objects that have very special properties.
And these properties are what ultimately lead to KP integrability.
Exactly.
Okay, this is all super interesting, but I think we're getting a little deep into the weeds here.
Right.
Maybe for now, let's just focus on this key point.
Okay.
That the leading terms of these non-perturbative differentials are these Krichever differentials.
Exactly.
And because these Krichever differentials are related to solutions of the KP hierarchy,
Yes.
that gives us a hint that the non-perturbative differentials themselves might also be KP integrable.
Absolutely. That's the core idea that the paper is exploring.
Okay, I think that's a great place to stop for now. In the next part of our deep dive, we'll take a closer look at how the authors actually prove this KP integrability.
Sounds good.
We'll explore some of the key properties of non-perturbative differentials like loop equations and the projection property.
Right.
And we'll see how these properties, along with some clever techniques like XY swap and dy-deformations, allow us to demonstrate the KP integrability of these fascinating mathematical objects.
I'm looking forward to it.
Me too. It's going to be a wild ride.
Yeah, it is.
So stay tuned.
Absolutely. All right, so we're diving back into these non-perturbative differentials and how to prove that they're KP integrable.
Yes, exactly. And you mentioned some pretty intriguing techniques last time, like X-swap and our dy-deformations.
Yes, those are really the key ingredients.
Okay, so let's start with X-swap. What's that all about?
So remember how we talked about topological recursion taking a Riemann surface and those two functions x and y as input?
Right.
Well, X-swap is exactly what it sounds like.
Right.
You swap the roles of x and y.
So it's like switching the labels.
Yeah, you can think of it that way.
And how does that help us with KP integrability?
The key is that this XY swap operation, it preserves KP integrability.
Oh, I see.
So if the differentials generated by the swapped data, so the Riemann surface with y now playing the role of x and vice versa, if those differentials are KP integrable, then the original differentials must also be KP integrable.
So like a mirror image.
Yeah. It's a kind of symmetry argument.
We're looking at the problem from a different perspective.
Exactly.
Yeah.
And sometimes that new perspective can make things much clearer.
So it's a way to simplify the problem.
In a sense, yes. It can transform the problem into something that's easier to analyze.
But what if, even after swapping x and y, it's still too complicated?
That's where those dy-deformations come in.
Okay, so tell me about those. What are we deforming exactly?
So we're deforming the differential of the function y, which we denote as decolty.
Okay.
And we're doing this near those special key points we talked about.
Right, the points where dx equals 0.
Exactly.
And why do we care about those points?
So in the standard setup of topological recursion, Daugherty is typically non-vanishing at those key points.
Okay.
But we can carefully deform Daugherty by adding a small correction term that's localized near a key point.
So we're tweaking Daugherty a little bit.
Yes.
Yeah.
But we're doing it in a very controlled way.
And what's the point of tweaking it?
The amazing thing is that these shady deformations, if they're done carefully,
they also preserve KP integrability.
Oh, wow. So we can change the problem, but the property we're interested in stays the same.
Exactly. It's like we're manipulating the puzzle pieces, but the overall picture remains intact.
And by manipulating those pieces, we might be able to make the KP integrability more obvious.
Exactly. We might be able to transform the problem into something we already understand.
So it's a combination of XY swap and these belly deformations that allows us to prove KP integrability.
Yes. The authors show that no matter how complicated the Riemann surface or the functions x and y might be, you can always find a sequence of these swaps and deformations
Oh, wow.
that will lead you to a known case where KP integrability is already established.
That's really clever. It's like a step-by-step process.
It is. It's a very elegant proof strategy.
Okay, but can we walk through a specific example?
Sure.
Just to see how these techniques work in practice.
Absolutely. So let's imagine a simple scenario.
We have a Riemann surface of genus 1.
Okay, so like a donut.
Exactly.
A hole.
Right.
Donut.
And let's say our function x has a single 0 at a point we'll call P on this donut, and y has a 0 at a different point Q.
Okay, so 1, 0 for x, 1, 0 for y on our donut.
Exactly.
Okay.
So we have our Riemann surface, our dxt, and the Bergman kernel.
Okay.
We feed all this into topological recursion and out pop these non-perturbative differentials.
But we don't know if they're KP integrable yet.
Right. That's what we're trying to prove.
Okay.
So we might start by performing an xy swap.
Okay, so now y has a 0 at P.
And x has a 0 at Q.
Right. We flipped them.
Exactly.
What does that give us?
It gives us a new set of non-perturbative differentials, those associated with this swapped data.
Okay.
And if these new differentials are KP integrable, then our original ones must be too.
Right, because of that symmetry argument. Okay, but what if even after swapping?
Yeah.
It's still too hard to figure out.
That's when we bring in the dy-deformations.
Okay.
Let's say the structure of those swap differentials is still really complicated. We can deform di by adding a small correction term near the point Q.
Which is now the 0 of x.
Right, after the swap.
Got it.
So we're tweaking dia near the 0 of x while making sure it's still well-behaved.
Right.
Meaning non-vanishing at the point P.
Which used to be the 0 of y.
Exactly.
Okay. So we're being very careful with our tweaks.
Yes, we have to be.
And by doing this, we're hoping to make the KP integrability more apparent.
Exactly. We might, for instance, deform dia to introduce an additional 0.
Okay.
At a point very close to Q. So now both d's x and d vanish at this new point.
But wait, I thought di wasn't supposed to vanish at the zeros of dx.
You're right. That's true in the standard setup of topological recursion. But remember, we're working in a generalized setup. Okay, so we have more flexibility.
Exactly.
Got it.
And by deforming nulity to introduce this extra 0, we can often guide the system towards a special configuration.
Okay.
Where that dual system of differentials, the one after the xy swap, becomes really simple.
And if that dual system is KP integrable, we know the original one must be too.
Precisely.
Yeah.
Because both xy swap and weighty deformations preserve KP integrability.
It's like we're solving a puzzle.
Exactly.
By rearranging the pieces until we see a picture we recognize. Amazing. Okay, before we move on, can we talk about those theta functions? You mentioned them earlier, but I'm still a bit fuzzy on what they are.
Okay, so theta functions, they're a special class of functions that have deep connections to lots of different areas of math, like complex analysis, algebraic geometry number theory, even physics.
Okay, they sound pretty important.
They are. They're very fundamental objects.
Yeah.
So what makes them so special?
One way to think about them is that they capture global properties of functions and differentials on Riemann surfaces. So Riemann surfaces can be quite complex, with multiple sheets and intricate branching structures. And theta functions provide a way to encode those global features in a really neat, compact form.
So they're like a summary of the Riemann surface.
You could think of it that way. And one key application of theta functions on Riemann surfaces is in constructing meromorphic functions, which are functions that are generally well-behaved, except for maybe having poles at certain points.
So like rational functions.
Exactly. Rational functions are the meromorphic functions on the simplest Riemann surface, the complex plane on more complex surfaces. We can use theta functions to build meromorphic functions with specific properties.
Like what kind of properties?
Like having zeros and poles at prescribed locations.
So we can control their behavior.
Yes. Precisely.
Wow, that's powerful.
It is. And their connection to non-perturbative differentials goes even deeper.
Oh, okay. How so?
Remember that projection property we talked about?
Vaguely.
Well, it turns out that those non-perturbative differentials can actually be expressed in terms of theta functions and their derivatives.
So theta functions are like a language.
Yeah. You could say that.
for describing these differentials.
Exactly.
That's fascinating.
And this connection is further strengthened
Mm-hmm.
by the fact that the leading term of those non-perturbative differentials
Right.
is given by the Krichever differentials.
Right, which are tied to the KP hierarchy.
Exactly.
Okay, so theta functions play a central role
Yes.
in both constructing these differentials.
And connecting them back to the KP hierarchy.
Wow.
It's all coming together.
It is a beautiful interplay of different concepts.
Okay. So we've covered a lot of ground here.
Yeah.
But I think we're ready for the final piece of the puzzle.
Those combinatorial formulas
Yes.
the paper mentioned.
Those are really fascinating.
I'm excited to hear about them.
All right. Well, let's take a break here, and we'll dive into those formulas in the next part.
Sounds good. I'm ready for more.
Me too.
Okay, so we've explored this connection between non-perturbative differentials and the KP hierarchy.
Right.
Using XY quas and dy-deformations.
Exactly.
And we even touched on these mysterious theta functions.
Yes. Those are key players in this story.
But you also mentioned some combinatorial formulas
Right.
that give us another perspective on these differentials.
Exactly. They provide a really neat way to understand the structure of these objects.
Okay, so tell me more about these formulas. What are they all about?
So you can think of these formulas as recipes
Okay.
for expressing those complicated, non-perturbative differentials in terms of simpler building blocks.
Okay.
And the ingredients in these recipes are special types of diagrams.
Diagrams.
Yeah, they're called Feynman diagrams.
Wait a minute, Feynman diagrams. I thought those were from physics.
You're right. They were originally developed to represent particle interactions in quantum field theory.
Yeah.
But it turns out that these diagrams, they have a surprisingly rich application in pure math as well.
Oh, wow. So what are they doing in this context?
Well, they provide a visual and systematic way
Okay.
to organize the terms that appear in the expansion of those non-perturbative differentials.
Okay, so instead of a big messy equation,
Yeah,
we get a picture.
exactly. And these pictures can be much easier to work with.
So can you give me an example of how these diagrams work?
Sure. Imagine a simple Feynman diagram with a few vertices connected by edges.
Okay, I'm picturing it.
Each vertex represents a particular type of differential,
Okay.
like those zazam we talked about.
Yeah.
And the edges represent how these differentials are combined.
Okay, so it shows how they interact.
Exactly.
It's like a blueprint for building up the differential.
That's really cool. So the diagram tells us how to put everything together precisely.
And why are these diagrams better than just using equations?
Well, for one thing, they make it much easier to keep track of all the terms when we expand those complicated expressions.
Right, it's easy to get lost in all those symbols.
Exactly. But with the diagrams, each diagram corresponds to a specific mathematical term.
Okay.
And by summing over all possible diagrams
Yeah.
that fit certain rules, we obtain the full expansion of the non-perturbative differential.
So it's a more organized approach.
Exactly. And often these diagrams can reveal hidden symmetries and relationships
Oh, interesting.
that would be very difficult to see from the equations alone.
So it gives us a deeper understanding of the structure.
Precisely.
Okay, this is all fascinating. But I have to admit, I'm still a bit fuzzy on how we actually construct these diagrams.
Right.
What are the rules?
It's a bit too involved to go into all the details here.
Okay.
But the basic idea is that each element of the diagram, the vertices and the edges,
Right.
they have specific rules associated with them.
Okay.
And these rules tell us how to assign mathematical expressions to each piece and how to combine them to get the overall expression for the differential.
So it's like a game.
Yeah? You could say
With very specific rules.
exactly. And the payoff is that these combinatorial formulas
Yeah.
expressed through these Feynman diagrams, they give us a really powerful tool for studying those non-perturbative differentials.
And revealing their secrets.
Precisely.
Wow, this has been an incredible journey.
It has.
We started with these non-perturbative differentials, explored their connection to topological recursion,
Right.
learned about XY swap and deformations,
Yes.
even delved into the world of theta functions.
Those are fascinating objects.
And now we have these elegant combinatorial formulas with Feynman diagrams.
It's amazing how it all comes together.
It really is. It's a beautiful example of the interconnectedness of math.
I completely agree.
So as we wrap up this deep dive, any final thoughts on the implications of this KP integrability result?
Well, remember, the KP hierarchy appears in so many different areas.
Right, from fluid dynamics to string theory.
Exactly.
It's everywhere.
And proving that these non-perturbative differentials are KP integrable suggests a profound connection between all those fields.
It's like a bridge.
Yeah, a bridge between different mathematical worlds.
That's a great analogy. And what does this bridge mean for future research?
Well, it opens up a whole new avenue for exploration.
Mm-hmm.
The techniques and insights from studying non-perturbative differentials
Yeah.
might shed light on problems in other areas.
Where the KP hierarchy plays a role.
Exactly, and vice versa.
It's a two-way street.
Precisely. A beautiful exchange of ideas.
Well, thank you so much for guiding us through this mathematical labyrinth.
It was my pleasure.
It's been an absolute privilege to learn from you.
Likewise.
And to our listeners, thank you for joining us on this deep dive into the world of non-perturbative differentials.
Keep exploring.
Keep questioning.
And never stop learning.
Until next time.
Absolutely.
Welcome to another deep dive. Today we're going deep into a paper that really caught my eye. It's called KP Integrability of Non-Perturbative Differentials.
Ah, yes, this one. It's quite a ride.
It is, and I thought it'd be great to unpack it together. Now, I know our listeners are pretty savvy when it comes to mathematical physics, but before we get into the nitty-gritty, maybe we can start with a bit of a level set. What exactly is KP integrability?
Right, so imagine you have a system. Could be describing waves, particles, all sorts of things, and you've got these differential equations. Often they're just a beast to solve.
Right, a total headache.
But then there's these special systems, these integrable systems, and they've got this hidden structure, almost like a secret harmony that makes them much easier to handle.
So like finding a shortcut through a maze.
Exactly. And KP integrability, it's named after this equation, the Kadomtsev-Petviashvili equation. It's a very specific type of this integrability. It pops up all over math and physics.
Okay, makes sense. So how do we even know if a system has this KP integrability? Is there like a test?
Yeah. There is. We can use something called determinantal identities. It's a bit technical, but basically you build these matrices from the system's equations, and then you see if certain determinants vanish.
Determinants, right. Those take me back to linear algebra.
Exactly. And it's like these determinants, they act as a fingerprint. They reveal if that special KP structure is hiding there.
Got it. Okay, now we're talking about differentials, and I remember them from calculus, but I'm a bit rusty on how they fit into this whole KP integrability thing. Could you give me a refresher?
Sure. Differentials, they capture change. They tell us how things vary. In this paper, we are looking at meromorphic differentials. They're a special type of function. They live on Riemann surfaces.
Riemann surfaces. I'm getting flashbacks to complex analysis.
Right. Think of them as these surfaces, but with a complex structure that allows us to define complex functions on them.
Okay, hazy memories coming back. But why are these meromorphic differentials so important for KP integrability?
They're key because many KP integrable systems can be described using them. This paper we're talking about, it focuses on a special kind called non-perturbative differentials. And these are constructed with something called topological recursion.
Topological recursion. Okay, that sounds interesting. What is it and how does it work?
Well, imagine you have this Riemann surface and you've got some special points on it. Topological recursion takes this geometric information and spits out a set of differentials.
So it's like a recipe. Geometric ingredients go in, differentials come out.
Yeah, that's a good way to think about it.
Okay, but what makes these non-perturbative differentials stand out?
They stand out because they bring quantum effects into play. They are defined as a kind of series with a parameter A, which is related to Planck's constant, and it controls the strength of the quantum stuff.
So they're like a bridge between the classical and quantum worlds.
Exactly. And that's part of what makes this paper so intriguing. It's looking at whether this KP integrability holds up even when we bring in these quantum aspects.
It's like testing the limits of this concept of KP integrability.
Exactly.
Cool. Now, there is a lot of specialized notation in the paper. Things like NIP for these non-perturbative differentials. Can you break down some of that for us?
Sure. So NIP, that's our non-perturbative differential.
Okay.
The N tells us how many points on the Riemann surface it depends on. And then there's the tau function. It's central to KP integrable systems. Think of it like a blueprint containing all the information about the system solutions.
The master key.
Got it.
Okay, I think we're starting to build a picture here. But what exactly are the authors trying to prove about these non-perturbative differentials?
They're setting out to prove that these differentials, even with all their complexity and those quantum elements, still exhibit this KP integrability.
That's a bold claim.
It is, and they use some incredibly clever techniques to prove it.
All right, so let's talk about how they set things up. They mentioned two setups, a standard and a generalized one for topological recursion. What's the difference?
The difference is all about what happens at those special points on the Riemann surface, the ramification points. It's all about the behavior of the functions x and y, which are like coordinates.
Okay, those ramification points seem pretty crucial.
They are. So in the standard setup, the differential dx vanishes at those points. In the generalized one, we relax that constraint, allowing more flexibility.
Okay, so it's like starting with a simpler case and then broadening things out.
You got it.
And what about those loop equations? They seem to pop up everywhere in this paper.
Ah, yes, the loop equations. They describe how the differentials behave as you move along a closed loop on the Riemann surface. They're like a set of rules that these differentials have to obey.
Traffic laws for differentials.
Yeah, kind of. And what's remarkable is that these loop equations, they hold true even for the non-perturbative ones, even with the quantum effects added in.
That's pretty mind-blowing. So even in the quantum world, there's still order. There's still structure.
Exactly. And that's just the beginning. There's a lot more to unpack, from the XY swap relation to the deformation formulas, and all of these pieces are going to come together to prove that big result, that KP integrability of these non-perturbative differentials.
All right, well, I'm definitely ready to keep going. This is getting really interesting.
Too. There's so much more to explore.
Okay, so you mentioned this XY swap relation. I'm all ears. What's that about?
So remember how x and y act like coordinates on the Riemann surface? Well, the xy swap relation, it explores what happens when you flip them. You essentially switch their roles.
We're changing our perspective.
Exactly. And the interesting thing is that even with this swap, there's still a connection between the non-perturbative differentials calculated using the original and swapped coordinates.
So there's some kind of relationship, even when we flip things around. What does that look like mathematically?
It's a formula, actually. It connects the original differentials to those calculated using the swapped coordinates. And it involves these derivatives with respect to y.
Derivatives again? It seems like they're popping up everywhere.
They are pretty fundamental. And in this case, those derivatives, they capture how the differentials transform under this coordinate swap.
I think I need an example. Can you walk me through a specific case, maybe with the 2MPM?
Sure. Let's say we have A2MP, which depends on 2 points. If we swap x and y, the new differential, let's call it A2NP, it can be expressed in terms of the original A2NP and its derivatives with respect to y. So you might have something like ATM y1 y2 equals A2MP y1 plus some derivative terms.
Ah, okay, so the swap differential isn't completely different. It's built from the original one and its derivatives.
Right. And that highlights the connection between these two seemingly different perspectives.
Okay, that makes more sense. Now, what about those deformation formulas? How do they fit into this picture?
Deformation formulas look at what happens when you slightly tweak the input data, like you nudge D a little bit.
So we're testing how sensitive these differentials are to changes in the input.
Yeah, that's a good way to put it. And there's a formula for that, too. It's a bit more involved. It uses things like residues, the Bergman kernel, and integrals.
Residues, Bergman kernel. Started to sound familiar.
But the point is, it tells you how those non-perturbative differentials change when you make these tiny adjustments.
I see. So the XY swap flips the coordinates, and the deformation formulas tell us how things change when we tweak the input data. It's all about exploring how these differentials respond to different kinds of transformations.
Exactly.
Before we get to the main event, the KP integrability proof, can we go back to the loop equations? You mentioned they apply to the non-perturbative differentials. What do they look like in this case?
Sure. They're similar to the standard loop equations, but there's a twist. Remember how these differentials have that parameter? Well, now the loop equations involve derivatives with respect to both v and r.
Okay, so they're like the souped-up version of the loop equations, handling both the geometric and the quantum aspects.
Precisely. And they're going to be key in showing that these non-perturbative differentials are indeed KP integrable.
All right, I'm ready for that proof now. Let's hear how they pull it all together.
All right, so the proof, it's quite elegant. It uses the XY swap relation, the deformation formulas, and the fact that a special kind of differential, called a Krichever differential, is already known to be KP integrable.
Okay, back up a bit. Krichever differentials. What are those?
Krichever differentials, they're like the classic example of a KP integrable system. They're well studied, and they act as a benchmark. They're built using the theta functions and the geometry of the Riemann surface.
Right. Theta functions, we've touched on those.
Yes. Now, the key here is that the leading term in the expansion of our non-perturbative differentials, when written in a specific way, it turns out to be exactly the corresponding Krichever differential.
So there's a direct link between them. Like the non-perturbative differentials are a generalization of the Krichever ones.
Exactly. And the authors exploit this link in their proof. They use the known KP integrability of Krichever differentials to show that these more general non-perturbative differentials are also KP integrable.
Okay, I'm starting to see the strategy. But how do they actually make that connection?
It's all about careful manipulation. They start with the generalized setup of topological recursion, remember, where there's more flexibility. Then they use the XY swap relation and the deformation formulas to gradually change the input data.
So they're strategically tweaking the coordinate system and the input step by step.
Yes, and each step is carefully chosen so that it preserves KP integrability.
That sounds tricky, like walking a tightrope.
It is delicate, but they make it work.
So where are they going with all these manipulations? What's the end goal?
The goal is to transform the problem into a form where the dual differentials, those calculated using the swapped coordinates, become Krichever differentials.
So they're trying to morph the problem into a scenario where they already know the answer.
Exactly. Because if they can show that the dual differentials become Krichever differentials, and Krichever differentials are KP integrable, then, by a property called duality, they've essentially proven that the original non-perturbative differentials are also KP integrable.
Okay, so it's like a chain reaction. They transform the problem step by step, preserving KP integrability along the way. Then they show that the transformed problem has a solution they already know is KP integrable. And because of duality, that means the original problem must also be KP integrable.
That's a great summary, and that's essentially how they prove their main theorem, the KP integrability of these non-perturbative differentials.
That's amazing. It's like a mathematical puzzle where all the pieces finally click into place.
It is. It's a beautiful example of how different mathematical concepts can work together to solve a really challenging problem.
I'm impressed. But wait, the paper also mentions a corollary, right? Something about extending this result to even more general cases.
You're right. The corollary says that even if you slightly change how those non-perturbative differentials are defined, as long as those changes don't mess up the KP integrability, then the resulting system will still be KP integrable.
So it's like saying the KP structure is pretty robust. It can handle some modifications without falling apart.
Exactly. And this flexibility, it's important for a couple of reasons. For one, it shows that KT integrability isn't tied to a single rigid definition of these differentials. And secondly, it allows us to bring back those KP times we talked about earlier.
KP times, right? Those generalized time coordinates. How do they fit back in?
Well, the corollary allows us to tweak those non-perturbative differentials in a specific way so that those KP times become part of their definition.
Okay, so we're essentially fine-tuning the recipe to incorporate those KP times.
Exactly.
So why are those KP times so important?
They're essential for understanding how these systems change over time, their dynamics, and long-term behavior.
I see. It's like we're adding a time dimension to our understanding of these differentials.
You got it.
Now, I know we've covered a lot of ground. Can we maybe do a quick recap of some of the key terms before we wrap up?
Of course. So we talked about the x-high swap relation, which tells us how things change when we swap coordinates. The deformation formulas, they tell us how things change when we tweak the input data. And those loop equations, they govern the behavior of the differentials, even the non-perturbative ones, taking into account both the geometric and quantum aspects. Then there's the proof itself, which relies on the connection to Krichever differentials and their known KP integrability. And finally, that corollary showing that this KP integrability is pretty robust, it can handle some modifications, and even allows us to bring those KP times back into the picture.
That's a lot to process, but I think I'm starting to get it. It's pretty amazing how all these pieces fit together.
It is. It's a really beautiful result.
Well, thanks for walking me through all of this. I feel like I've gained a much deeper understanding of this paper and the whole concept of KP integrability.
It's been my pleasure. It's always exciting to share the beauty of mathematics with someone who appreciates it.
And to our listeners, stick with us for the final part of our deep dive. We're going to explore the broader implications of this research and what it means for the future of mathematics and physics.
It's going to be a fascinating discussion.
All right, so we've dug deep into the math, but I'm really curious about the bigger picture. What does this proof of KP integrability for these non-perturbative differentials actually mean? Does it change anything or open up new possibilities?
Oh, it definitely does. The authors actually talk about this towards the end of the paper. The implications go way beyond this specific result.
Okay, give me the big picture. What kind of impact are we talking about?
Well, think about integrable systems. KP integrability, it's a tool, right? It helps us solve these complex systems. And by proving that these non-perturbative differentials with all that quantum stuff baked in are KP integrable, it's like we've expanded the territory of what's integrable.
So it's not just a classical physics thing anymore. It extends into the quantum realm.
Exactly. It suggests that KP integrability, this hidden structure, it might be even more fundamental than we thought.
Okay, that's pretty mind-blowing. So what does that mean for actual research? What new doors does this open?
For one, we can start looking at KP integrability in quantum field theories. That's a whole new playground.
Quantum field theories. That's where things get really weird, right?
They do, but that's where the fun is. And KP integrability could give us new ways to tackle those theories, understand things like elementary particles and fundamental forces.
Okay, so big implications for physics. But what about math itself? Does this have an impact outside of integrable systems?
Absolutely. Remember, these differentials, they're built using topological recursion. And topological recursion, it's got its fingers in a lot of pies. Algebraic geometry, knot theory, even number theory.
Wow, it's like a mathematical butterfly effect. One little flap of the wings here, and it causes ripples all over the place.
That's a great analogy. For example, there are these spaces called moduli spaces. They parameterize geometric objects. Topological recursion is used to study them. And these results, they could give us a whole new understanding of these spaces.
So it's not just providing answers, it's generating new questions, new directions to explore.
Exactly.
Okay, and there's one more thing you keep mentioning. Generalized, blobbed, topological recursion. What is that and how does it fit in here?
Right. So remember, blobbed topological recursion, it's like adding these extra bits of information, these blobs, to the Riemann surface.
Like adding decorations, making things even more complex?
Yeah, that's it. Now, generalized blob topological recursion, it's like taking the best of both worlds, the flexibility of the generalized setup and those extra blobs. It's like a supercharged version of topological recursion.
A power-up. Okay, I'm intrigued.
And the authors, they suggest that their findings, especially with those loop equations, hint that there's a connection to this generalized framework.
So this paper, it's not just the end of the story. It's a jumping off point for even more research.
Absolutely. Generalized, blobbed, topological recursion. It's a pretty new area, a lot of potential there.
Like a whole new continent to explore. What kind of problems could this help us solve?
Well, quantum field theories, especially those with gauge symmetries, they're really tough to handle. This framework could give us the tools we need to crack them open.
So it's like giving physicists a new set of tools, a new way of looking at things.
Exactly. And it might not just be physics. String theory, condensed matter physics, even statistical mechanics, they could all benefit from this.
Wow, it's amazing how this one paper can have such far-reaching implications.
Yeah.
It really shows how interconnected all these different fields are.
It does, and that's one of the things I love about mathematics.
Well, I think we've covered a lot of ground today. We've gone from these very specific non-perturbative differentials all the way to the frontiers of mathematical physics and beyond. It's been a wild ride, but a really rewarding one. I feel like I've learned so much.
It's been my pleasure to guide you through it. And to all our listeners out there, keep those brains buzzing, keep exploring, keep asking questions. Who knows what other amazing discoveries are waiting out there?
That's right. And that's a wrap for today's deep dive. Until next time, keep on diving deep. Welcome to today's deep dive. It's going to be a wild one. We're going deep into advanced mathematics this time.
Always exciting.
Always. We'll be looking at this paper, KP integrability of non-perturbative differentials. Quite a title.
It is.
The authors are Alexandrov, Bychkov, Dunin-Barkowski, Kazarian, and Shedrin.
A great team, and they really are tackling some super intricate stuff here. Concepts that have been, well, basically just conjectured for years, you know?
And they're even hinting at some connections to Generalized blob topological recursion.
Now, that's something I want to hear more about.
Me too. But let's not get ahead of ourselves. First, let's break down some basics. What exactly is KP integrability, specifically when it comes to systems of differentials?
Okay, good place to start. So we're dealing with a system of these differentials. We denote them as hun, where it can be any positive integer.
Okay.
And each hun represents a differential with unvariables.
Got it. Got it.
Now, KP integrability for this system, how do we figure that out? Well, we use a special determinantal identity. It's kind of like a test.
A test. So we're checking if the system has this special property.
Exactly. And this identity, it involves constructing what we call a bi-half differential. It's denoted by A1.
Got it.
And this A1, it captures how 2 points on a Riemann surface interact.
Ah, Riemann surfaces. Takes me back to grad school.
Haha, yeah, those can be tricky, but super important here. Now, here's the test. If the determinant of a matrix, and this matrix is formed using A1, if that determinant equals un for all that are 2 or greater, then bam, our system is KP integrable.
Okay, so we've got determinants, we've got this bi-half differential, all happening on a Riemann surface. There's a lot to keep track of. But what does it all mean? Like, why should we care about KP integrability?
Ah, the big question. Well, KP integrability has a very close connection to the tau function. You've heard of that, right?
I have.
And the tau function is like this super powerful tool. We use it to solve those KP equations, that whole family of partial differential equations.
Right.
And, those equations pop up everywhere. Fluid dynamics, string theory, you name it.
So this KP integrability thing, it's not just some abstract idea. It actually has real-world connections.
It does. It helps us understand and solve some pretty important problems. Now, to really grasp KP integrability, we got to talk about a specific type of differential. It's called a Krichever differential. They're basically fundamental in building solutions to those KP equations, like the essential ingredient.
Okay, got it. So Krichever differentials are key to this whole KP integrability thing. And KP integrability helps us solve these KP equations, which have, like you said, all these applications in different fields. But hold on. How do we even get these differentials in the first place? I know the paper mentioned something called topological recursion.
Right, you're on the ball. Topological recursion, it's like this amazing tool, almost like a recipe. We use it to generate these systems of differentials.
Recipe. Sounds intriguing. What are the ingredients?
Okay, so we need a few things. First, a Riemann surface. Then we need 2 special functions. We usually denote them as x and y. And finally, we need a specific type of differential called a bidifferential.
So by changing these ingredients, we can get different systems of differentials.
Absolutely. We can tweak the recipe and see what comes out. Now, the authors, they go a step further. They introduce these concepts of key points and something called key points on our Riemann surface.
Key points. Interesting. What do those do?
Well, they kind of act like control knobs. They influence the properties of those differentials that topological recursion spits out.
Like they shape the output of the recipe.
Exactly. They can affect things like where the poles are located, those points where the differential kind of explodes. And they also influence those periods of the differentials.
Periods, right. Just a quick refresher. What are those again?
Okay, so imagine you're integrating the differential, and you're doing this along a closed loop on the Riemann surface. The period is the value you get from that integral. It's like a global snapshot of the differential's behavior.
Got it. So topological recursion uses these key points to, fine-tune those systems of differentials it creates. Okay, that's all starting to click, but we're still missing the stars of the show here, those non-perturbative differentials.
You're right. We've been setting the stage. Understanding topological recursion is crucial because these non-perturbative differentials, well, they're built on top of it. They're these special mathematical objects, really key to understanding systems that are, complex, and systems that we can't solve easily using those, traditional methods.
All right, let's get to the heart of the matter then. What are these non-perturbative differentials? What makes them so special?
Well, they're expressed as a series and a parameter we call edgegon. You can think of as this small number, almost like a zoom lens. It lets us look at the differential at different scales.
Okay.
And the thing is, unlike a lot of systems in physics, these guys don't represent just a simple perturbation around a known solution.
By perturbation, you mean like a small nudge to a system that we already understand pretty well.
Exactly. We can analyze a system after the nudge, and it's usually just a small deviation from what it was.
Right.
But these non-perturbative differentials, they're more intricate, more complex. They don't fit into that simple framework.
Sounds like things are about to get really interesting. So These differentials are expressed as a series, with that wrapper parameter letting us zoom in and out. What else can you tell me about their structure?
Well, here's the kicker. The leading term in the series, when it is really small, it's actually a Krichever differential. Remember those?
Yeah, the building blocks for solving the KP equations.
You got it. So we're already seeing connections here.
The leading term of these non-perturbative differentials links back to those Krichever differentials, which we need for KP integrability. It's all coming together.
It is. And a key focus of this paper is to figure out if these non-perturbative differentials are also KT integrable. If they are, it could be a huge E. It could change how we solve those KP equations and how we understand those complex systems that are governed by them.
Okay, I'm definitely hooked now. Tell me, what kind of properties do these non-perturbative differentials have? Did they give us any clues?
They do. First off, they satisfy something called loop equations. Think of these equations as constraints. They kind of dictate how the differential behaves.
So like rules that the differential has to follow?
Exactly. And they also satisfy a modified version of what we call the projection property. It basically tells us how to break down the differential into simpler pieces.
Okay, so we have loop equations and this modified projection property. How do those help us? Do they play a role in figuring out if these differentials are KP integrable or not?
They do. They're important for their own sake, but also because they're super important in the proof of the main theorem of this whole paper.
Oh, I can't wait to hear about that theorem. But before we get there, the authors mention an XC swap and dy-deformations. What are those all about?
Those are pretty clever techniques, I gotta say. They use them to analyze the differentials. The XY swap, it basically means switching the roles of our X and Y functions, the ones from that topological recursion setup. And dy-deformations involve very carefully tweaking the Y function.
So they're kind of playing around with the X and Y functions, swapping and tweaking them. But why?
Well, turns out these manipulations help us prove certain properties of those non-perturbative differentials. And they're absolutely essential for the big reveal, the main theorem.
All right, you've got me on the edge of my seat. Spill it. What's the theorem? Are these non-perturbative differentials KP integrable or not?
The answer is yes. The main theorem of this paper states that systems of non-perturbative differentials are indeed KP integrable.
Wow, that's a major breakthrough. It's been a conjecture for over a decade, right?
That's right. And this paper finally gives us the proof.
That's amazing. But I have to admit, I'm still a little fuzzy on how they actually proved it. It sounds like a lot of really intricate manipulations and transformations.
Oh, it is. The proof is quite complex, I'll give you that. It involves cleverly deforming the input data we use in topological recursion, using those XY swaps and dy-deformations we talked about. But the key is they do all of this while making sure that the KP integrability property stays intact the whole way through.
So they're carefully manipulating the system step by step, like walking a tightrope, always making sure they don't lose that KP integrability until they reach a point where they can say, boom, we know for sure that these non-perturbative differentials are KP integrable.
You got it. It's really a testament to their mathematical brilliance.
This is incredible, but I'm sure we've only scratched the surface here. There's so much more to uncover in this paper.
You're telling me. We've laid the groundwork, we've got the key concepts down, but now it's time to roll up our sleeves and dive deep into the nitty-gritty of the math behind these fascinating non-perturbative differentials.
I'm ready.
Welcome back. So last time, we set the scene, right? We talked about those non-perturbative differentials, those mysterious objects that might just hold the key to unlocking solutions for some really, really complex equations.
Yeah, it was a whirlwind tour.
Yeah.
Differentials, KP integrability, topological recursion. We covered a lot of ground. And the big takeaway, the main theorem of the paper proves that those non-perturbative differentials, they are KP integrable. Big news.
Huge. And today we're going to dig deeper, like really get into the nitty-gritty of what these objects actually are. So the authors, they start by defining non-perturbative disconnected half differentials. We denote them as nlin.SI.
Okay, I got to be honest, even the name is a bit intimidating. NN half differential. Can we break that down a bit for those of us who, haven't been living, breathing this stuff for the past decade?
Sure. So the NA, that part tells us we're dealing with differentials involving two sets of n variables. Makes sense.
Okay, yeah.
And the term half differential, that indicates that these objects, they involve square roots of differential forms. It might sound a bit strange, but it's a way to capture more subtle geometric information, you see.
Square roots of differentials, huh? All right, I'm willing to go with it. So we've got these n-span things. But what's with the n? What's that all about?
Good catch. Sharp eye. That notation, it signifies that these are what we call the disconnected versions. Now, the paper uses a really cool visual tool to help us understand all this. They use graphs.
Graphs, like
Well,
with nodes and edges and all that.
exactly. Imagine a graph, right? And it has different types of nodes. First, we got multi-leaves. Those represent multiple variables.
So like if our differential has 3 variables, we'd have 3 multi-leaves on the graph.
Spot on. Then we have these O-vertices. They correspond to those differentials that we get from topological recursion, remember? The ums.
Right, the output of our mathematical recipe for making differentials.
Exactly. And lastly, we have something called vertices. These guys represent the theta function. It's a function that's deeply connected to the geometry of those Riemann surfaces we talked about.
Okay, so 3 types of nodes, each representing a key element. Got it. What about those edges connecting them? What do they mean?
Those edges, they represent the operations that link all these components together. For instance, an edge between a multileaf and an O-vertex, that might show us an integration operation. Now, the important thing is, in the disconnected version, Antimarin, some of these nodes, they might just be hanging out on their own, not linked to anything.
Like a network where some points are floating around, not connected.
Exactly. But the authors are really interested in something called the connected and half differentials. These are denoted by NPN.
Okay, so in MPNN, everything is connected, like a fully linked network.
Precisely. And we get from the disconnected to the connected version using a tool called the inclusion-exclusion principle. Have you heard of it?
I have.
It's a way to count elements without counting anything twice. It's pretty clever. In our case, it helps us go from those isolated, disconnected objects to a fully connected structure. We're essentially building complexity from those simpler pieces.
So it's like we're taking those disconnected components and weaving them together into a fully linked structure, making sure we don't accidentally overcount any of those mathematical relationships.
Perfectly put. Now, these connected NPNs, they're crucial because they're the building blocks for something we call extended differentials, denoted by WEPA NPN.
Hold on. So we're going from NPN to NPN to NPN. It's like a chain of transformations.
That's a great way to think about it. Each step gets us closer to those non-perturbative differentials, NPN, that we're ultimately interested in.
So how do we get from those NPN to the NPN?
Well, from NPN, we get another set of extended differentials, NPND. And from those, we finally arrive at our non-perturbative differentials, NPN, NPN. We do this by setting some auxiliary variables to 0. It's like we're fine-tuning our focus to the most important aspects.
Wow, that's quite the journey. We start with disconnected half differentials, apply the inclusion-exclusion principle, construct extended differentials, and then boom, we get those non-perturbative differentials. There's a lot to keep track of.
It is, but those graphs we talked about earlier, they really help us visualize the whole process. Those multi-leaves, those vertices, those thumb vertices, all connected in specific ways, they give us this visual map of the structure of FunPN.
It's like those graphs are the key to deciphering this whole complex mathematical code.
Exactly, and they're not just pretty pictures, you know? They actually play a key role in proving those important properties of FunPN that we mentioned earlier, the loop equations and that modified projection property.
Right, those act like the rules that govern how FunPN behaves,
Yeah.
right? And they also give us a way to break it down into simpler parts. But why are they so crucial for proving that FunPN is KP integrable?
That's where the brilliance of the authors really shines. They use these properties, along with those XY swaps and dy-deformations, to demonstrate that ConPN is indeed KP integrable. They manipulate the system in this incredibly clever way that keeps the KP integrability property alive through the whole process.
So it's like they're master puppeteers, carefully controlling every string, making sure everything works in perfect harmony.
That's it, and their goal. It's to transform the initial system, step by step, into this special case where we already know that KP integrability holds true.
So they're reverse engineering the problem.
Yeah.
Working backward from a solution that's already been cracked. That's pretty slick.
It is. They're aiming for a scenario where the x function has poles, those points where it goes to infinity, of very high order at the zeros of the y function.
Okay, remind me again, what are poles?
Think of them as points where the function just blows up, explodes to infinity. The higher the order of the pole, the more dramatic that explosion is.
Got it. So they manipulate the system to create these dramatic blow-ups in x at the exact points where y touches 0. What's so special about that setup?
Well, in this particular scenario, if we look at the dual system, which means swapping x and y, things become a lot simpler. It actually boils down to a well-studied case involving those Krichever differentials we talked about before.
Ah, the building blocks of KP integrability. So by transforming the system into this special case, they connect unpn to those Krichever differentials, right?
You got it. And since we already know that Krichever differentials are KP integrable, this connection basically confirms that unpn must also be KP integrable. Pretty clever, huh?
I'm blown away. It's so elegant. But this whole proof, it relies on what you called the standard setup for topological recursion, right? What exactly does that mean?
Good point. In the standard setup, the x function has simple zeros. It touches 0 neatly, no funny business, and y is well behaved near those zeros. It's finite, doesn't jump around or anything. This makes the analysis a lot easier.
But what about cases where those specific conditions on x and y don't hold?
The authors thought of that too. They show that these more general cases, we can actually treat them as limits of the standard setup.
Limits. Like getting closer and closer to something without actually reaching it.
Exactly. We tweak the system, making those poles of x get closer and closer to infinity, but we keep everything else behaving nicely. And they prove that even when we do this, even in these more general situations, that KP integrability property, the one we so carefully preserved in the standard setup, it stays with us.
So their proof isn't just limited to specific cases, it extends to a whole bunch of systems.
You got it. It makes their findings much more powerful and applicable. Really impressive stuff.
This deep dive has been mind-blowing. We've gone through so much math already. I'm excited to see how it all comes together in the final part of the proof.
Me too. Let's finish this exploration strong.
Welcome back. It feels like we've been exploring this intricate maze of mathematics. I'm really curious to see how it all comes together in this final part.
I know, right? It's been a wild ride. We covered so much ground. We talked about those key concepts, the importance of KP integrability, and those intricate non-perturbative differentials. PN, remember those?
Oh, I do. And we learned that the authors actually managed to prove that these PNs are indeed KP integrable. That's a big deal. It has so many implications for different fields. But I'll admit, the specifics of how they did it are still a bit fuzzy for me.
That's what we're going to tackle now. The author's proof, it's like this beautiful tapestry woven from two main threads. First, we have that standard setup of topological recursion. And second, they use this very carefully constructed sequence of transformations.
Okay, let's untangle those threads one by one. You mentioned the standard setup in part 2. It's all about those specific conditions on the functions x and y that we feed into topological recursion, right?
Exactly. In the standard setup, x has simple zeros. It means it crosses the zero line cleanly, no weird stuff happening, and a y. Well behaved near those zeros of x. It's finite, no jumps, no drama.
So those conditions on x and y make things simpler. But how do they help with the proof?
They're essential because in this standard setup, we have this awesome property. Both the x, y swap a and d, certain ways we can deform y, they both preserve KP integrability.
Ah, yes. Those transformations. The xy swap, where we switch the roles of x and y, and those dy-deformations, where we carefully tweak y.
You got it. And the beauty of it is, even though we're messing with the system using these transformations, that KP integrability, it sticks around. Throughout the whole process, it's like we're changing the system's clothes, but its heart stays the same.
I love that analogy.
Yeah.
So they're strategically manipulating the system, always being super careful not to break that KP integrability until they reach this point where they can say, aha, we know for sure that this is KP integrable.
Precisely. It's a brilliant strategy. They're working backward from a known solution.
Okay, so what's that special case they're aiming for? What does it look like?
They want to transform the system into this scenario where x, our function x, has poles of very high order. You know, those points where the function explodes to infinity. And they want these poles to happen exactly at the zeros of the y function.
Ah, poles. And the higher the order, the bigger the explosion, right?
Exactly.
Yeah.
So they're creating these dramatic blowups in x at the exact spots where y touches 0.
That's a pretty specific setup. Why is that so helpful? Why is that a known case of KP integrability?
Because, get this, in this special case, if you look at the dual system, which means swapping x and y, things become much, much simpler. It actually reduces down to a case that's been studied a lot, and it involves those Krichever differentials we talked about earlier, remember?
Of course, the building blocks for solving those KP equations. So they're connecting those non-perturbative differentials, PN2, to Krichever differentials by transforming the system into this special case.
Exactly. And since we know Krichever differentials are KP integrable, well, that connection confirms that the PNs have to be too. It's like a chain reaction of integrability.
Wow, it's a really clever strategy. But this whole proof depends on that standard setup of topological recursion, right? what happens when those conditions on X and G don't hold? Those simple zeros and well-behaved behavior. What about all the other cases?
That's a great question. The authors, they tackled that too. They showed that these more general cases, we can think of them as limits of the standard setup.
Limits, like approaching something without actually getting there.
Exactly. Imagine tweaking the system bit by bit. Those poles of X, we make them get closer and closer to infinity. But everything else, we keep it nice and well-behaved. The authors showed that in this limiting process, KP integrability, that precious property we preserve so carefully in the standard setup, it stays with us.
So even in those more general cases, KP integrability still holds true. That's really impressive.
It is. It shows how robust their proof is. It applies to a much wider range of systems than just those specific cases.
This deep dive has been amazing. We started with all these complicated concepts, differentials, KP integrability, topological recursion. It felt like a whole new language. But we took it step by step, and now we're here. We've seen the intricate structure of those non-perturbative differentials and those remarkable properties they have.
And that proof, it's a masterpiece of mathematical reasoning. The authors guide us through this intricate dance of transformations, always making sure that KP integrability stays center stage. It's like watching a grand symphony unfold, each note perfectly placed.
I couldn't agree more. This paper is a fantastic example of how mathematicians can approach these complex problems. Developing new techniques, crafting elegant solutions is truly inspiring.
It really highlights how interconnected different areas of mathematics are. We saw Riemann surfaces, theta functions, the inclusion-exclusion principle. They all played a part in this amazing mathematical story.
It's been a true pleasure having you as our guide through this mathematical landscape. Thanks for sharing your insights and knowledge with us.
The pleasure was all mine. I always enjoy exploring the beauty and complexity of math.
And to our listeners, thank you for joining us on this deep dive. We hope you enjoyed the journey as much as we did.
Keep those minds curious.
Welcome to the deep dive. Today we're diving deep into mathematical physics with a paper titled KP Integrability of Non-Perturbative Differentials.
Yeah, it definitely sounds complex, but I think we can break it down.
Yeah, it's going to be a really interesting deep dive.
I think so too. Essentially, the paper explores some deep connections between a mathematical structure called KP integrability and a method called topological recursion.
Okay, so can you remind me what exactly KP integrability is? I know it has something to do with systems of differentials, but...
Yeah, absolutely. So in mathematical physics, KP integrability is a special property of differential forms.
Okay.
Imagine like a collection of these forms. We can denote them by a hun, where n can be any positive integer.
Really?
And these hun are special functions called meromorphic n differentials, and they live on a Riemann surface.
Okay.
Now, a Riemann surface, you can think of it as like a two-dimensional surface, like a sphere or a donut, but it can have multiple holes or handles,
Right.
and we call that the genus of the surface.
Right. I remember Riemann surfaces,
Yeah.
from topology.
Exactly.
So what exactly makes a system of these differentials KP integrable?
That's a good question. The key is how these differentials relate to each other.
Okay.
So a system of differentials is KP integrable if they satisfy a very specific relationship.
Okay.
And we express that through a determinantal identity involving a special bi-half differential.
Okay.
We'll call that A1.
A bi-half differential. That sounds a little unusual.
It is. It's kind of a unique object.
Yeah.
So think of it as a function of 2 points on our Riemann surface.
Right.
It's called a half differential because when it transforms under changes of coordinates, it involves square roots of the Jacobian determinant.
Right.
And the bi part is because it depends on 2 points.
Okay, so bi-half differential. Got it.
Exactly.
So this A1 is important then?
Yes. It acts as a generating function for all the other differentials in the system. You can think of it as like a master key.
Right.
That unlocks the structure of all the hun.
Okay, so A1 is a central figure here.
Yes, definitely.
But how does this determinantal identity actually work?
Well, the paper expresses this in equation 3.
Okay.
And it essentially states that the hun can be written as a determinant of a matrix.
Okay.
And the elements of this matrix are constructed from the second derivatives of A1.
So if we can express un in this determinant form, then we know it's KP integrable.
That's right.
Okay, but why is this property so important? What does it actually tell us?
Yeah, that's a great question. KP integrability has profound implications.
Okay.
Systems that are KP integrable have remarkable properties.
Like what?
For instance, they often admit an infinite number of conserved quantities,
Oh, wow.
which means that there are certain quantities
Estimated.
associated with the system that remain constant over time.
Right.
So this makes them highly predictable and solvable, even when describing complex nonlinear phenomena.
So it's like a cheat sheet for solving these complex systems.
Exactly.
No wonder it's a big deal. Now, the paper also mentions tau functions
Yes.
in connection with KP integrability. Can you shed some light on those?
Absolutely.
What are they?
Tau functions are fascinating. They appear in a lot of areas,
Okay.
including integrable systems and algebraic geometry.
Hmm.
They act as a generating function
Oh.
for solutions to certain types of differential equations.
Okay.
And in the paper, equation 5
Right.
establishes a connection
Okay.
between a system of differentials and a tau function.
Mm-hmm.
We'll denote that by.
Okay.
And essentially the derivatives of the tau function,
Yeah.
with respect to certain variables, encode information about the differentials.
So these tau functions are another layer of structure on top of our system of differentials.
Exactly.
Okay.
They provide a powerful framework for analyzing and understanding solutions.
Now, the paper introduces the concept of extended differentials,
Yes.
got called disconnected and called connected, and relates them back to our original on.
Right.
Why do we need these extended versions?
So these extended differentials help us dig deeper into the structure of KP integrability.
Okay.
While the original on capture essential relationships, the extended versions reveal a more intricate web of connections.
So we're upgrading our tools.
Precisely.
Let's get a more refined view of the system.
Exactly. And the paper provides explicit formulas for these extended differentials
Where?
in equations 7, 8, and 9,
Okay.
showing how they're constructed from combinations of the original on and their derivatives.
Okay. And then equations 10 and 11 seem to reformulate the KP integrability condition using these extended differentials.
You're absolutely right.
Okay.
Those equations rewrite the KP integrability condition in a more compact way. By using these extended differentials, we can express the relationships between the Han
Right.
in a more elegant form.
So it's not just about having KP integrability.
Yeah.
It's about understanding its deeper structure. And the extended differentials provide a powerful lens for doing that.
Precisely.
Okay. Now, before we go into non-perturbative differentials,
Yes.
I think it's worth mentioning an example of a KP integrable system.
Yeah.
Krichever differentials. Have you come across those before?
Of course. Krichever differentials are a classic example of a system that has KP integrability.
Oh, okay.
They play a crucial role in the construction of the non-perturbative differentials.
I have, but to be honest, they've always been a bit of a mystery to me.
Oh, okay.
Can you be a quick refresher?
Of course. So Krichever differentials are a specific type of differential form that are constructed using certain geometric objects on a Riemann surface.
Okay.
And we need three things.
Okay.
A Riemann surface, a line bundle on that surface, and a point on the surface. Now think of the line bundle as attaching a vector space to each point on the surface.
I'm picturing that. So how do we actually get a differential form from this?
So the Krichever differential arises from a section of the line bundle.
Okay.
This section vanishes at the chosen point on the Riemann surface with a particular order. Now, the derivative of this section, when viewed as a one form on the surface, is what we call the Krichever differential.
Interesting. So it's like we're capturing the local behavior of the section near the chosen point.
Precisely. And the order of vanishing of the section at the point determines the properties of the Krichever differential. So the higher the order, the more complex the differential.
Okay.
And these Krichever differentials, constructed in this way, automatically satisfy the conditions for KP integrability.
That's amazing.
Yeah, it's quite remarkable.
Okay, so they're like a concrete example
Yes.
that helps us understand this abstract concept of KP integrability.
Exactly.
Okay. This is incredibly helpful.
Yeah.
Now I feel much more prepared to tackle topological recursion and see how it all fits together.
It's a remarkable connection, and we'll unravel it step by step.
Okay.
Let's start by understanding what topological recursion is.
Okay.
Imagine a mathematical machine.
Wait. Before we jump into topological recursion, I'd love to delve a bit deeper into the mathematical details of how those Krichever differentials are constructed.
Okay.
They seem to be quite important.
Yeah, they are.
And I want to make sure I have a solid grasp of them before we move on.
You're absolutely right.
Okay.
It's important to have a strong foundation.
Yeah.
So let's break down the construction
Okay.
of Krichever differentials.
Okay.
They are built upon a Riemann surface,
Right.
a line bundle on that surface, and a point on the surface.
Right. We said that.
Yes, exactly. Think of the line bundle as attaching a vector space to each point of the surface.
Okay, I'm picturing that.
Okay, good.
So how do we actually get a differential form from this setup?
The Krichever differential arises from a specific section of the line bundle. And this section is chosen such that it vanishes at the chosen point on the Riemann surface with a particular order.
Okay.
Now, the derivative of this section, when viewed as a one-form on the surface, is what we call the Krichever differential.
Interesting. So it's like we're capturing the local behavior of the section near the chosen pole.
Precisely.
Okay.
And the order of vanishing of the section at the point determines the properties of the Krichever differential.
Okay.
The higher the order, the more complex the differential.
And these Krichever differentials constructed in this way automatically satisfy the conditions for KP integrability.
Yes, that's the remarkable thing. Their construction ensures that they exhibit KP integrability, making them a valuable tool for understanding this concept.
This is incredibly helpful.
Good.
Now I feel much more prepared to tackle topological recursion and see how it all fits together.
Great. Now let's finally dive into that mathematical machine we call topological recursion. Picture this. It's like a machine, you know. It takes geometric data as input, and through a recursive process, it churns out a system of differential forms.
Okay, that does sound intriguing. So what kind of geometric data are we feeding into this machine?
The basics. A Riemann surface, and then also two meromorphic functions on that surface.
Okay.
We typically call those x and y.
Okay, so x and y are defined on the surface.
Right, exactly. And remember, meromorphic functions can have poles.
Right, those points where the function blows up.
Exactly, they blow up to infinity.
So those poles are really important then.
They are very important because they define what we call the key points of the topological recursion. So in the standard setup, these key points are the zeros of the differential dx.
Okay.
So the points where dx vanishes.
Okay.
And at these key points, d has to be what we call well-behaved.
Okay, so what does well-behaved mean in this context?
It means that at those key points, d is regular, meaning it doesn't blow up, and non-vanishing, meaning it's not zero.
So it's finite and non-zero.
Right, exactly.
Okay, so I'm picturing these key points on our Riemann surface.
Okay.
So how does the recursion actually work? How do we get those differential forms?
So it starts with an initial set of differentials.
Okay.
Typically duo 1 and TO 2.
Okay.
Which are determined by the input data.
So that's the Riemann surface and the x and y.
Yes, exactly. And then we have a recursive formula, which is given by equation 18 in the paper.
Right.
And this allows us to compute higher order differentials, which we denote by OGN, where G is a non-negative integer, representing the genus, and N is a positive integer.
Okay, so G is for the genus of the Riemann surface.
Right.
And N is just an index.
Yes, exactly.
So we're building up these differentials starting from the ground level.
And going up level by level.
What's the main idea behind this formula?
It's all about residues.
Okay.
Calculating residues of certain expressions involving the lower order differentials at the key points.
Okay.
And remember, residues capture the behavior of a function near its poles.
Right.
So at each step of the recursion, we're taking information from the poles of these differentials at the key points.
Right.
And using that to construct the next level of differentials.
That's really cool. So we're zooming in on those poles.
Yes.
And using them as building blocks to create these more intricate forms.
Exactly. It highlights how topological recursion uses the geometric and analytic properties of these objects to generate a system of differentials.
Now, the paper mentions loop equations and a projection property in connection with topological recursion.
Yeah.
Can you remind me what those were all about?
Absolutely. So the loop equations are a set of constraints that these differentials have to satisfy.
Good.
They involve certain combinations of the differentials, which are denoted by WGN.
Okay.
And they essentially ensure that these combinations behave nicely near the key points.
Okay, so they're like quality control checks.
Yes, exactly.
And make sure our differentials are well behaved.
Exactly. They impose important conditions on the structure of these differentials,
Right.
ensuring they have the right properties for applications.
Okay, what about the projection property?
Yeah, the projection property is another crucial aspect of topological recursion. It states that we can reconstruct the entire differential subgene just by knowing its behavior near the key points.
So it's like we can figure out the shape of a mountain range just by looking at the peaks.
That's a good analogy. It highlights the power of the projection property.
Right.
It tells us that the key points contain all the essential information about the differential.
Okay, now the paper mentions an XY swap.
Yes.
In topological recursion. What is that?
So the XY swap is a symmetry operation in topological recursion.
Okay.
Remember, our input data included those two functions, x and y.
Right.
Well, the XY swap simply involves switching their roles. We swap x and y and see what happens.
So it's like flipping a coin and seeing what's on the other side.
Exactly.
So does this swap change the differentials that we get?
It does lead to a different set of differentials.
Oh, okay.
But these new differentials are related to the original ones in a very specific way. The symmetry highlights the deep structure underlying topological recursion and provides insights into the relationships between the differentials.
So far, we've talked about KP integrability and topological recursion as separate concepts. How do they actually connect?
That's the crux of this paper.
Okay.
And it's where things get really interesting.
Okay.
The paper starts by making a surprising observation.
Okay.
It turns out that the differentials generated by traditional topological recursion are only KP integrable when our Riemann surface has genus 0.
Can you remind me what genus 0 means again?
Of course. The genus of a Riemann surface basically tells us how many holes it has.
Right.
So a sphere has genus 0.
Okay.
A donut has genus 1.
Right.
And so on.
Okay, so the paper is saying that if our Riemann surface is more complex, like a donut or something even more wild, the differentials we get from traditional topological recursion won't be KP integrable.
Exactly. That's where these non-perturbative differentials come in.
Okay, this is where it gets interesting. So how do these non-perturbative differentials work? How are they defined?
They're defined as a formal power series in a special parameter, which we denote by ejong. You can think of it as a small number that allows us to expand our differentials and explore their behavior.
So 8 is like a magnifying glass, letting us zoom in on the structure of these differentials.
Precisely. And what's fascinating is that the leading term in this expansion is actually a Krichever differential.
Oh, wow.
Which we discussed earlier.
Right.
This is stated in lemma 3.4 and given explicitly in equation 49.
Okay, so we're starting to see the connections. It's like these non-perturbative differentials are built upon those familiar KP integrable Krichever differentials.
Exactly. It's as if the Krichever differentials are providing the foundation. And then we're adding on more layers, more terms in the expansion to capture the complexities of higher genus Riemann surfaces.
This is starting to make more sense now.
Good.
The paper defines these non-perturbative disconnected half differentials.
Yes.
In definition 3.1, given by equation 43.
Right.
It's a very dense equation.
It is.
Involving a lot of different mathematical objects. Can we break it down a bit?
Yeah, of course. So these disconnected half differentials, denoted by NBA, are the building blocks for constructing our non-perturbative differentials.
Okay, so they're like the ingredients in the recipe.
Exactly.
For these non-perturbative differentials.
Precisely.
What are those ingredients? What's in this recipe?
So equation 43 shows us that these half differentials are constructed using prime forms, theta functions, the able map, and the differentials from topological recursion.
So we're mixing elements from different mathematical universes.
We are. It's quite fascinating.
Yeah, to create these new objects.
Exactly.
So KIP, KRS, N are like steps. To bridge the gap between topological recursion and the KP integrable Krichever differentials.
Yes, that's a great way to think about it. They provide a way to combine insights from both of these worlds. To extend KP integrability to more complex surfaces.
This is starting to come together. So what's the next step? What do we do with these non-perturbative differentials?
Well, the next stage is to explore their properties and see if they behave like we expect.
Okay.
In particular, we want to see if they satisfy those loop equations
Okay.
and the projection property we talked about earlier.
So we want to make sure they fit nicely
Yeah.
into the framework we've already established.
Exactly.
So do they.
We'll find out. That's what we'll explore next as we go deeper into the paper and see how these non-perturbative differentials behave within the standard setup of topological recursion.
So we've laid the groundwork, explored KP integrability, those Krichever differentials, and topological recursion. We've even constructed these non-perturbative differentials to handle those more complex Riemann surfaces. Now the big question is, do they actually work? Do they have the properties we're looking for?
That's the exciting part, seeing how it all comes together. The paper looks at this question in the standard setup of topological recursion. Remember where the key points are the zeros of dx.
Right, and Korsty has to be well behaved at those points.
Exactly. So Theorem 3.7 states that these non-perturbative differentials still satisfy those loop equations we discussed.
So they're passing the first test, fitting nicely into the framework.
Yeah, exactly.
Can you remind me what those loop equations tell us again?
Sure. Remember, they impose constraints on the differentials involving those WGG Aaron terms.
Yeah.
And they make sure those combinations behave nicely near the key point.
So they're like making sure those differentials are well behaved, no nasty singularities at those key points.
Precisely.
And the fact that our non-perturbative differentials satisfy them is a good sign.
It is. It means they're behaving as we expect.
This is encouraging. What about the projection property? Does that hold for these differentials too?
That's where things get a little more subtle. Theorem 3.9 introduces a modified version of the projection property specifically for these non-perturbative differentials. It's given by equation 53.
Okay.
It involves those Petviashvili terms having vanishing A periods.
Can we go over A periods again?
Of course. So picture our Riemann surface with its holes like a donut.
Yeah.
Imagine drawing closed loops around those holes.
Okay.
Those are the A cycles.
Okay.
Now, the A period of a differential form is the integral of that form along one of those A cycles.
So we're measuring the total effect as we travel along that loop.
Exactly. And this modified projection property says that a specific combination of our non-perturbative differentials integrates to 0 along those A cycles.
Why is this modified property important? What does it tell us?
It constrains their behavior, and it connects to something called blobbed topological recursion.
Blob topological recursion. What are these blobs?
There are additional terms that we add to the recursion to handle more complex situations. You can think of them as modifications or perturbations.
Okay.
And in this case, the blobs are those Krichever differentials.
The ones that are KP integrable.
Exactly.
So we're adding those as extra ingredients to our topological recursion recipe.
That's a great way to put it. They allow us to handle more complex scenarios like those higher genus Riemann surfaces.
So they're like spices, making our dish more flavorful and capable.
That's a fantastic analogy. Now remember those XY swaps and deformations we talked about?
Yeah.
Those are actually crucial for proving the KP integrability of these differentials.
Oh, so why are they important for proving KP integrability?
The key is that both the XV swap and the deformations of Betty preserve KP integrability. Meaning if we start with a system that's KP integrable and apply these operations, the result will also be KP integrable.
So we have these special moves
Exactly.
we can use to reshape our system without breaking that property.
Right. And the strategy is to use those transformations on our non-perturbative differentials to show they must be KP integrable.
Okay, I'm getting a sense of the game plan. Can you walk me through how this proof works?
The paper details this in section 4.6. The first step focuses on the standard setup. The goal is to deform dx and dy in a specific way until we get a special configuration.
What's so special about this configuration?
We want dx to have poles of high order at the zeros of that.
Okay, so we're strategically making those high-order poles. What's the point of that?
It turns out that when dx has these high-order poles, the dual system, denoted by xg, becomes very simple.
Okay.
All the differentials in the stable range vanish.
They become 0.
Yes. And this lets us directly connect our non-perturbative differentials to those Krichever differentials.
So by making these high-order poles, we simplify the dual system and reveal its connection to those KP integrable Krichever differentials.
Exactly. It's like stripping away the complexity to see the underlying structure.
That's really clever. So we connect our non-perturbative differentials to those simple Krichever differentials, and since KP integrability is preserved, our original system must also be KP integrable.
Precisely.
But wait, The paper proves KP integrability for the generalized setup as well, not just the standard one. How do they handle that?
That's where limits come in. The paper uses previous research to show that the generalized setup is a limit of the standard setup. Basically, we can approximate those more complex cases with simpler systems.
Okay, so it's like taking snapshots,
Yeah.
each closer to the full picture.
Exactly.
And since each snapshot is KP integrable, the final picture must be too.
Precisely. And here's the crucial point. KP integrability is a closed condition, meaning that if we have a sequence of systems, each KP integrable, and they approach a limit, that limit will also be KP integrable.
So it's like this property is really resilient.
Yes, it survives even as we push our systems to the limit.
That's powerful. So the paper shows that the non-perturbative differentials are indeed KP integrable.
Yes. Theorem 3.13, given by equations 57 and 58, captures this result.
What an incredible journey. We went from KP integrability to those Krichever differentials and topological recursion. And finally, we proved that these non-perturbative differentials, designed for those complex Riemann surfaces, are also KP integrable.
It's a fantastic example of how we can use abstract math to uncover hidden connections.
Exactly. This is just the beginning. This paper opens up so many new possibilities. How will this impact our understanding of quantum systems? What new insights might we gain into the nature of spacetime?
The possibilities are endless. This is what scientific inquiry is all about.
And that's what the deep dive is about, taking you on these journeys of exploration. So keep questioning, keep exploring, and keep diving deep.
We'll see you on our next deep dive.
Hey there, deep diver. Ready for a deep dive into some pretty dense math.
Sounds good.
We're talking KP integrability and non-perturbative differentials.
Oh, yeah, some really cool stuff.
And we've got an awesome paper to guide us today by Alexandrov, Brichakov, Dunin-Borkowski, Kazarian, and Shadrin. They're tackling a pretty challenging conjecture, proving that these non-perturbative differentials, which pop up in areas like topological strings and matrix models,
Right.
actually fit within the KP framework.
It's a big deal. It's like they found the missing piece of a mathematical puzzle.
A missing piece, I like that. But before we get too excited, let's take a step back. What exactly is KP integrability?
Well, think of it this way.
All right.
It's like having a superpower that lets you predict how certain systems evolve over time.
Ooh, superpower. Nice.
Yeah.
Hmm.
Like imagine you're trying to model, let's say, ocean waves crashing on a shore. If your system is KP integrable, you've got a set of mathematical tools, the KP hierarchy, that can unlock the secrets of those waves. You can predict their motion with amazing precision.
So it's like a crystal ball for math problems.
Exactly. A crystal ball for certain mathematical systems.
Okay, I'm starting to get it. But where do these non-perturbative differentials fit into all of this? They sound pretty complex.
They are complex, but essentially they're a way to enrich our mathematical models, making them more robust and less dependent on the specifics of the problem at hand.
So it's like developing a universal language for math.
Yes. A universal language that can describe a wide range of phenomena.
I like that, a universal language for math. Okay, but how do we know these non-perturbative differentials actually speak the language of KP integrability?
That's where this paper comes in. These researchers have managed to prove that these differentials, which are defined as formal power series in a parameter, are indeed KP integrable.
Formal power series.
Yeah, and they did it using some really clever techniques like the XY swap and a special type of mathematical deformation.
Okay, now you're really piquing my curiosity. What's the XY swap all about, and how does it help us prove KP integrability?
So imagine you have a system defined by two differentials, dx and dy. The XY swap, like the name suggests, just swaps their roles. The ingenious part is that this seemingly simple operation actually preserves KP integrability. It's like looking at the system from a different angle without changing its fundamental properties.
So it's like flipping a coin and finding out it's still heads or tails, just from a different perspective.
Exactly.
Okay, I get the analogy.
Mm-hmm.
But how does that help us prove anything?
Well, by strategically applying this swap, along with some carefully chosen deformations, the researchers could transform the original problem into a simpler one whose KP integrability was already known.
Ah, so they're simplifying the problem without changing its essential nature. Clever.
Very clever.
But the paper also mentions something called graphical formulas. What are those, and how do they come into play?
Graphical formulas are a way to visually represent these complex mathematical objects. Think of them as circuit diagrams, where each component represents a mathematical object, and the connections between them represent their relationships. These diagrams can be super helpful in understanding how different elements of the system interact.
So it's like turning abstract math into a picture, making it easier to grasp.
Exactly. It's a visual aid to help us understand the math.
Now, the paper also delves into some pretty heavy-duty concepts like loop equations and the projection property.
Oh yeah, those are important.
Can you give us a taste of what those are all about?
Think of loop equations as a set of rules that constrain the behavior of these non-perturbative differentials. They're like boundaries that define the allowed solutions. The projection property, on the other hand, helps ensure that these differentials are uniquely determined, meaning there's only one possible solution that fits the bill.
Okay, so they're like the detectives of the mathematical world narrowing down the suspects until they find the one and only culprit.
Huh. That's one way to put it. They help us make sure we're on the right track.
So how do they actually use these tools to prove KP integrability?
Well, that's where the real magic happens. By carefully analyzing the graphical formulas, applying the constraints imposed by the loop equations, and leveraging the uniqueness guaranteed by the projection property, they could piece together a rigorous proof. They showed that these non-perturbative differentials do indeed fit within the KP framework.
Okay, I think I'm starting to get the big picture here, but the paper also dives into some specific mathematical formulas, right? What can you tell us about those?
Sure. You're talking about the formulas for n, fine, phime, and y and p.
Yes, those are the ones.
These represent different types of non-perturbative differentials, and they involve summations over certain sets of graphs. Each graph captures a particular configuration of mathematical objects and their relationships, contributing to the overall expression for the differential.
So they're like different recipes for building these differentials.
Exactly, each with its own set of ingredients and instructions.
Okay, I like that analogy. So how do these formulas help the researchers prove their point?
The researchers meticulously dissect each term in these formulas, using properties like vanishing A periods. These tell us how certain differentials behave when integrated along specific paths.
So it's like they're analyzing every ingredient and step in the recipe to make sure the final dish turns out perfectly.
Exactly. And they also use residue calculations, which involve analyzing the behavior of functions near their singularities or poles.
It sounds like they're pulling out all the stops using every tool in their mathematical arsenal to crack this problem.
They absolutely are. And that's what makes this paper so fascinating. It's a beautiful example of how researchers can combine graphical intuition with rigorous mathematical analysis to achieve a truly remarkable result.
I'm ready to dive deeper into the nitty-gritty of those proofs. What say we move on and explore how they actually use these techniques to demonstrate KP integrability in the standard setup of topological recursion?
Let's do it. Welcome back to the deep dive.
Okay, so we left off talking about those loop equations.
Right. And remember, they act like constraints on the system, right?
Yeah, like setting the boundaries for how these non-perturbative differentials can behave.
Exactly. And the researchers use that graphical formula for W.
W subscript N a P.
Yep, which represents one type of these differentials.
Okay.
To prove these loop equations hold true.
Ah, those crazy graphs with their multi-leaves and
Oof,
vertices,
yeah.
vertices.
I know, right?
It's wild how they can be translated into actual mathematical arguments.
It's pretty amazing. The researchers really go deep, analyzing the structure of those graphs and applying the properties of the differential.
Which decorate each vertex.
Exactly, yep. And those decorations represent different types of differentials, each with its own information about the system.
Right, so by looking at the graph and using what they know about those differentials, they can show that WW subscript NP again.
Yes, satisfies the loop equations.
It's like proving a theorem by, like, arranging building blocks.
Yeah, that's a great analogy. And proving the loop equations is key because satisfying them is necessary for KP integrability.
Okay, so it's like step one in proving this property.
Exactly, passing the first test. Now, what about the projection property?
Oh yeah, that sounded pretty important for figuring out the values of those non-perturbative differentials.
It is, because it ensures those differentials are uniquely determined. There's only one solution that fits all the criteria. And to prove this, they use the graphical formula for UMP.
Okay.
But this time, they add another variable to the mix.
Making the graph even more complex.
Yep, but there's a good reason. By analyzing this modified graph and using a key property of certain differentials, they're vanishing A periods.
Hold on, rewind a bit. What are A periods again? And why does their vanishing matter so much?
Sure. So think of A periods as a way to measure how differentials behave when we integrate them along certain closed paths. If the A period vanishes, it means the integral along that path equals 0, which tells us something important about the differential itself. Okay. So knowing that certain differentials have vanishing A periods helps them prove the projection property.
Exactly. It's like a special characteristic of these differentials that lets them fit perfectly within the constraints of the system.
Okay, that makes sense.
So the projection property, along with the loop equations, provide this really powerful framework for establishing KP integrability.
Because they give us the necessary and sufficient conditions.
Yep.
Now let's talk about that XY swap, that technique that lets us view the system from different perspectives. How did the researchers actually use it?
It's really clever. Remember, it involves exchanging the roles of dx and dd, and this operation, importantly, preserves KP integrability.
Right, like flipping a coin and seeing it's still heads or tails, just from a different angle.
Exactly.
But how does this help them prove KP integrability?
Well, they combine the XY swap with the loop equations and the projection property.
Okay.
Remember, we can deform both dx and I in a controlled way without messing up KP integrability.
Right, like carefully adjusting settings on a machine. Exactly. So by applying a series of XY swaps and deformations, they can transform the original problem into a simpler one where KP integrability is already established.
So they're making the problem easier to solve without actually changing it.
Exactly.
But what exactly are they aiming for with these manipulations?
Good question. They're aiming for a system where dx has poles of a certain order, a sufficiently high order, at all the zeros of the die.
Okay, sounds pretty specific.
Yeah.
Why is that important?
Because it has big implications for what we call the dual system of differentials, which is what we get by doing that XY swap.
So they manipulate the original system to get a specific structure in its dual counterpart.
Exactly. And this particular setup, where dx has high-order poles at the zeros of die, forces all the differentials in the stable range of the dual system to vanish. They essentially become 0.
Okay, so they're simplifying the dual system by messing with the original one.
Right.
But why is this vanishing of differentials so important?
Because it reduces the dual system to a known KP integrable form. It's like clearing away all the clutter to see a simple structure underneath.
So they simplify the dual system, prove its KP integrability, and then what?
Then they just reverse the XY swaps and deformations they did earlier, taking them back to the original system. But now they know the original system must also be KP integrable because they were careful to preserve that property throughout.
So they go on this round trip, confirming KP integrability in a simpler realm and bringing that knowledge back to the original problem.
Exactly. It's a brilliant strategy. It really shows the power of mathematical reasoning.
This is so cool.
Right.
But I'm curious, how does their proof work for the generalized setup of topological recursion? We've been talking about the standard setup so far.
Great question. And the extension is actually pretty straightforward.
Oh, really?
Yeah. The key is that the system of differentials in the generalized setup can be viewed as a limit of a family of systems in the standard setup.
So they can approximate the generalized system using a bunch of standard systems.
Precisely. And because we already know KP integrability holds for the standard setup, and that this property remains true even in the limit.
They can conclude that the generalized setup is also KP integrable.
Exactly. It's like inheriting a trait from your parents.
Okay, I get it. Now, we've talked a lot about these graphical formulas and how they represent those complex differentials.
Yeah.
But how do they actually come into play in the proofs?
Oh, they're essential. Those formulas give us explicit representations for those non-perturbative differentials. They're like blueprints showing exactly how those differentials are constructed.
Right, they're like a visual roadmap. But how do the researchers actually use them in the proofs?
They basically dissect each term in the formulas using things like vanishing A periods.
Okay.
Remember, those tell us how certain differentials behave when integrated along specific paths.
Right.
They also use residue calculations, which involve analyzing how functions behave near their singularities or poles.
So it's this blend of visual intuition from the graphs and hardcore math analysis.
Exactly. It's a beautiful mix of intuition and rigor. And through this careful analysis, they can show that those loop equations and the projection property hold true, leading to the proof of KP integrability.
This is incredible. I'm really impressed with how they approach this, but are there any actual practical applications for this research?
Oh, absolutely. While the paper itself focuses on the theoretical side, the implications go far beyond that.
Okay, like what?
Well, Understanding KP integrability has huge implications for studying and modeling complex systems in various fields, from fluid dynamics to financial markets, even string theory.
So this abstract math concept could help us understand real-world phenomena.
Yes. KP integrability suggests a deep underlying structure in these systems, which allows us to develop more accurate and efficient models.
Amazing. But what about the bigger mathematical picture? Does this research open new doors in other areas of math?
For sure. The techniques they developed, especially the graphical formulas and the interplay of xi swaps and deformations, have the potential to be used for all sorts of math problems.
So it's not just about solving this one conjecture. It's about developing new tools and approaches for mathematics as a whole.
Exactly. This work shows just how creative and interconnected math can be.
This has been a wild ride.
Right.
I'm really excited to explore the broader implications of this research and dig into some of the questions it raises.
Me too. Let's wrap things up in the last part of our deep dive.
Okay, so we've covered a lot of ground, exploring those intricate graphical formulas, the loop equations, the XY swaps, and those deformations.
It's been quite a journey.
But what does this proof actually mean for math, for understanding these complex systems?
It's a big step. Proving those non-perturbative differentials are KP integrable gives us some seriously powerful tools to analyze, to predict.
For a wide range of systems, you mean?
Yeah, we're not just talking about abstract mathematical objects here. This has real implications.
Like real-world applications.
Absolutely. Think about, well, ocean waves, how chaotic they are. Or financial markets constantly fluctuating, even weather patterns, so complex. All of these are systems that could potentially be modeled and understood using KP integrability.
Wow, so this could actually help us, say, predict the weather more accurately.
Yeah.
Or understand the stock market better.
Potentially, yeah. KP integrability suggests there's this underlying structure, this order within these seemingly chaotic systems. It's like we're finding a hidden code that helps us see how they work.
That's incredible. Okay, so we've talked about those practical applications, but what about the bigger picture in math itself? Does this research open up new avenues in other areas?
Oh, definitely. The techniques they developed, especially those graphical formulas and that clever dance between XY swaps and deformations,
Right.
they have the potential to be applied to all sorts of mathematical problems.
So it's not just about solving this one conjecture. It's about providing new tools and approaches for math in general.
Exactly. This work shows how creative and interconnected different areas of math can be.
Now, the paper focused on a specific type of mathematical object, those non-perturbative differentials. Can you remind us what those actually are?
Sure. Think of differentials as a way to capture those tiny changes in a system. They tell us how things vary when we make those tiny adjustments.
Okay.
Non-perturbative differentials, specifically, are defined as, well, formal power series and a parameter. And they show up in various areas like topological strings, matrix models.
So they're like these little probes letting us examine how systems behave at a really fine scale.
That's a great analogy. And what this paper does is prove that these non-perturbative differentials have this remarkable property, KP integrability.
And to refresh our memory, what does it mean for something to be KP integrable?
Essentially, it means the system can be described by a set of equations called the KP hierarchy. And these equations let us predict how the system will evolve over time.
Got it. So this paper shows that those tiny probes of change can be understood, can be predicted using the framework of the KP hierarchy.
Exactly. And this has major implications, especially in mathematical physics.
Let's talk about those implications. How does this research connect to our understanding of the physical world?
Well, for starters, KP integrability is closely tied to the theory of integrable systems, which are systems that have these really neat mathematical properties. We can find exact solutions to their equations of motion without having to use approximations.
So it's like having a perfect lens, letting us see those systems without any distortions.
Exactly. And that's huge for understanding fundamental physics. In areas like string theory and quantum field theory, where getting exact solutions is super difficult.
The paper also mentions background independence, which sounds important. What's that about, and how does it relate to this research?
Background independence is this key concept in some physics theories, especially in things like quantum gravity. It's about formulating theories that don't depend on a fixed background space-time.
So like the laws of physics should be the same no matter where you are or what's around you.
Precisely. And the findings of this paper, with their introduction of multi-KP times, offer a way to achieve this background independence for certain systems. These multi-KP times are basically extra variables that help us describe the system in a way that doesn't rely on any specific background.
That's fascinating. So this research isn't just about understanding these mathematical objects, it's also potentially laying the foundation for new theories in physics.
Exactly. And like with any breakthrough, this paper doesn't just answer questions, it raises new ones too.
Yeah, what are some of those new questions? What mysteries are left to be solved?
Well, one big question is, can we extend these techniques to even more complex systems? Maybe systems with an infinite number of degrees of freedom.
That sounds challenging.
It is. Another exciting direction is to explore the role of these non-perturbative differentials in specific physical models. Could they provide new insights into things like quantum gravity, black holes, even the early universe?
So much left to explore. It's amazing how an abstract mathematical proof can have such far-reaching implications, impacting how we understand everything from the tiniest particles to the vastness of the cosmos.
It really shows the power of human curiosity and the elegance of mathematical reasoning. And who knows what other secrets we'll find as we keep exploring.
Well, this deep dive has been a mind-blowing journey. Thanks for joining us.
It's been my pleasure.
Until next time, keep exploring the fascinating world of knowledge and discovery.